Welcome to Relaxing Wisdom. Settle in. Let your shoulders drop a little lower than they are right now. There is nothing you need to do for the next while except listen, and even that you are allowed to let go of whenever sleep decides to take you. Tonight, we are going somewhere very old and very slow, somewhere that has been moving the entire time you have been alive, the entire time anyone has been alive, and it has never once paused for breath. Beneath you right now, the ground is moving, not in any way you can feel, not in any way you will ever feel in a single lifetime, but it is moving all the same, with a patience that makes the word patience seem too small. The continents are drifting across the surface of the planet at roughly the speed your fingernails grow. Think of that for a moment. The slow, quiet, almost invisible creep of a fingernail over weeks and months, the kind of growth you only notice when it is suddenly time to trim them again. That is the pace at which whole land masses, with their mountains and their rivers and their cities and their sleeping people, are sliding across the face of the earth. Somewhere between 2 and 10 centimeters a year. The Atlantic Ocean, the wide grey water between the Americas and the coasts of Europe and Africa, is growing wider as you lie here by something like 2 to 2.5 centimeters every year. About the width of your thumb. Every year, a thumb's width more sea between two shores that were once pressed tightly together. It does not sound like much, a thumb's width. But the thing about this slow drift is that it never stops, and it has never stopped, and time, given enough of itself, turns the smallest motion into something almost unimaginable. 2.5 centimeters a year, carried forward across 200 million years, opens an entire ocean thousands of kilometers wide. The grandest gulf you can picture between two continents began as a crack you could have stepped across, widened only at the pace of a growing fingernail, and given enough patience, enough deep, dreaming time, became an abyss. That is the first thing I want you to carry with you into sleep tonight. Slowness is not stillness. The slowest things in the world are often the most unstoppable. Before we go further, I would love to know where in the world you are listening from tonight, whether it is dark outside your window or whether the light is just beginning to soften, whether you are somewhere near one of these wide oceans or far inland. Leave a word in the comments and tell me the name of the place that is holding you while you rest. And if you are new here, if you have only just found this quiet corner, you might want to subscribe gently so that more of these slow journeys can find their way to you on the nights you need them. There is no rush. The comment will keep until morning. For now, just let the idea of the moving ground settle over you like a heavy, warm blanket, and let me walk you slowly into the story. Because here is the strange and beautiful truth at the heart of tonight. The Earth does not simply let its continents wander aimlessly forever. Over enormous spans of time, far longer than any empire, far longer than the whole story of our species, the continents are drawn together. They gather. They crowd against one another until almost all the dry land on the planet has merged into a single, vast, sprawling mass. And then, after holding together for a while, that great mass begins to break. It splits, it rifts, the pieces drift apart across the widening seas, until once again the land is scattered around the globe in separate fragments. And then, slowly, inevitably, they begin to gather once more, assemble, shatter, drift, reassemble, over and over and over, like a planet breathing in and breathing out, like a heartbeat measured not in seconds but in hundreds of millions of years. You may have heard somewhere along the way of one of these gathered worlds. You may have heard the name Pangaea, perhaps in a classroom long ago, perhaps in a half-remembered diagram of all the continents fitted together into one ragged shape, with South America tucked snugly against the curve of Africa. Pangaea is the famous one. It is the one that gets drawn in the textbooks, the one most people can name if you ask them whether the continents were ever joined. And it is real. It was real. But here is the thing that almost no one is ever told, the quiet secret that turns the whole familiar story inside out. Pangaea was not the first. Pangaea was not the only. Pangaea was simply the latest. It is only the most recent verse of a song the planet has been singing for at least 2 billion years. There were supercontinents before Pangaea and supercontinents before those, gathering and breaking in the dark, long before there were eyes to see them, long before there was a single creature crawling on the land. Pangaea is the one we remember best only because it is the most recent, the freshest set of footprints in the snow, the one whose traces have not yet been entirely erased. Behind it, fading back into deep time, stand others. And in front of it, still unformed, waiting somewhere in the future beneath our feet, another is already gathering, and it already has names. But we will come to that. We have all night. For now, let me give you the first vivid clue. The first piece of evidence that the ground beneath us is not as settled as it pretends to be. I want you to picture 3 mountain ranges very far apart, scattered across the surface of the world as it is today. Picture, first, the Appalachian Mountains. The long, soft, ancient spine of green hills and worn ridges running down the eastern side of North America. They are old mountains, rounded and gentle, their sharp peaks long since smoothed away by hundreds of millions of years of rain and frost and patient erosion. They roll quietly through forests, gathering mist in their valleys. Now picture, across the wide Atlantic, the Caledonides. The highlands of Scotland, the rugged uplands that march on through Scandinavia, through Norway, reaching toward Greenland. Stone and heather and cold, clear lochs. Mountains worn down by the same slow forces, with the same ancient, weathered look about them. And now picture, further south still, on another continent entirely, the anti-Atlas mountains of Morocco. Dry, sunlit ridges of folded rock rising out of the edge of the great deserts of North Africa, the warm stone glowing under a southern sky. 3 mountain ranges, 3 continents, 2 oceans between them. And yet, when geologists look closely at the rock, at the way the layers are folded, at the ages and the structures and the very grain of the stone, they find the same mountains, not similar mountains, the same mountains. The Appalachians, the Caledonides, and the anti-Atlas were once a single, continuous, unbroken chain. One great range of peaks marching across one piece of land, raised up together in the same vast collision of continents, and then the land beneath them tore apart. An ocean opened down the middle of that mountain chain slowly at the pace of a growing fingernail and carried the broken pieces away from each other across millions of years until they came to rest where they sit today, on separate shores, separated by water, each one looking like its own private wilderness, none of them remembering that they were once a single ridge of stone. Let that picture stay with you for a moment. A mountain range torn into 3 and scattered across the world. The hills of Appalachia, the highlands of Scotland, the desert ridges of Morocco, all of them the same broken bone of a vanished giant. That is the kind of clue that first told us the continents had moved. That is the kind of clue that lets us rebuild worlds that no longer exist. And the world those mountains belonged to was Pangaea. Let me tell you a little about it, slowly, so that you can build it in your mind as you drift. Pangaea came together gradually, the way these things always do with the continents of an earlier scattered world creeping toward one another across closing oceans. By somewhere around 335 to 300 million years ago, the gathering was largely complete. Almost all the land on Earth, nearly every piece of it, had crowded together into one enormous supercontinent, a single landmass so vast that you could, in principle, have walked from what is now the far north to the deep south, from one edge of the world to the other, without ever once crossing the sea. The name Pangaea was given to it much later by a man named Alfred Wegener in the year 1912. We will spend more time with Wegener later in our journey because his story is a quiet tragedy and a quiet triumph both, and it deserves to be told slowly. But for now, simply know that he reached back into the old Greek words and chose a name that meant, more or less, all the earth, all the land, all one piece. Pangaea. The whole world's dry ground gathered into a single shape, and around that single shape of land there was a single shape of water. One ocean, vast beyond anything we know today, wrapping almost the entire planet. The continents we live on now share the world's water between several named oceans, the Atlantic, the Pacific, the Indian, and the rest. But in the time of Pangaea there was essentially one enormous global sea encircling the gathered land. It too was given a name from the Old Greek, Panthalassa, all sea. Just as Pangaea meant all the land, Panthalassa meant all the water, the single world ocean rolling around the single world continent in unbroken immensity. Picture that if you can. A planet seen from far away with one great patch of land and one great expanse of blue wrapped around it, no familiar shapes, none of the coastlines you would recognize, just the all land and the all sea, turning slowly in the dark. And along one side of Pangaea, on its eastern flank, the ocean reached inward in a great curving bay, a gulf that pressed into the body of the supercontinent like a bite taken out of an apple. This embayment had its own name too, the Tethys Ocean, a warm, broad arm of water cradled in the eastern curve of the gathered land. So you have the picture now slowly forming. The supercontinent Pangaea, all the land in one, around it Panthalassa, all the sea, and reaching into its eastern side, the embracing curve of the Tethys. A whole world, complete and strange, and utterly gone now, broken and scattered into the continents and oceans you would recognize on any map today. But what was it like, this gathered world? What would it have been to stand upon it? Here is something that I find quietly astonishing, and I offer it to you as something soft to turn over in your mind as the night deepens. When you gather almost all of the world's land into a single enormous mass, you create something the scattered continents of today simply cannot have. You create an interior, a deep, vast, landlocked heart, thousands of kilometers from any coast in every direction. And the trouble with being thousands of kilometers from any coast is that the rain can never reach you. Rain, after all, comes from the sea. The water rises from the warm ocean as vapor, gathers into clouds, and is carried inland by the winds, falling as it goes. But it falls as it goes. By the time those winds have crossed hundreds, then thousands of kilometers of dry land, they have long since wrung themselves out. The moisture is gone, and so the deep interior of Pangaea, that immense central region so far from any shore, became one of the driest places the surface of the earth has ever known. A vast continental desert stretching for thousands of kilometers, baked and parched and silent, a dryness on a scale that simply does not exist on our scattered world today, because no piece of land today is large enough to have a heart so far from the sea. And the climate of Pangaea did something else, something with a rhythm to it that I find almost lulling to describe, because such an enormous landmass heats and cools differently from the surrounding ocean. It generated tremendous seasonal swings, great reversing winds that geologists call a mega monsoon. A monsoon, you may know, is the seasonal turning of the winds that brings a wet season and a dry season, the great rains that arrive and then depart. Pangaea had this, but magnified by its sheer size into something colossal, a mega monsoon. For part of the year, the winds would turn and lash the margins of the supercontinent with torrential seasonal rains, the coasts drenched while the interior stayed dry. And then the winds would reverse, and the rains would retreat, and the seasons would turn the other way. A planet-sized breathing of wet and dry, year after year, across the whole vast body of the land, the wet flank and the bone-dry heart, the breathing rains at the edges and the silent desert at the center. Hold that image gently. A single continent so large it made its own weather. A desert at its heart so deep no rain could reach it. A monsoon at its edges so vast it had to be given a name all its own. This was the most recent gathered world, the latest verse of the planet's long song, and even it, the freshest and best remembered of all the supercontinents, is utterly gone. It held together for a while, this Pangaea, this all the Earth, and then, around 200 million years ago, in the early part of the age we call the Jurassic, it began to do what every supercontinent before it had done. It began to break. It did not break suddenly. Nothing on this scale is ever sudden. It began with rifts, with cracks, with long valleys tearing open across the land where the crust was being slowly pulled apart. And into those rifts eventually the sea came in. New oceans were born in the splitting of the old continent, narrow at first, mere channels of water in the widening cracks, then broadening at the pace of a growing fingernail, year by year by year, until the pieces of Pangaea were no longer one land but many, drifting apart across seas that had not existed before. The Atlantic Ocean that I told you about at the very beginning, the one still widening by a thumb's width every year, is one of those young oceans, born in the breaking of Pangaea, still opening, still carrying the pieces of that vanished world further and further apart even now, even tonight, even as you breathe. So you see why Pangaea is the one we know best. Its breakup is recent in the planet's terms. The young oceans born from its shattering still exist. The sea floor that recorded its splitting is still down there, much of it holding its evidence. The torn mountain ranges, the Appalachians and the Caledonides and the Anti-Atlas, still stand where they were carried, still recognizable as the broken pieces of one chain. Pangaea left a relatively fresh trail, and we can follow it. But this raises a question, and it is the question I want to leave you with as we close this first part of our journey and prepare to go deeper. It is one of the open doors we will walk through together later, so let it hang quietly in your mind. If Pangaea broke apart and the pieces are still drifting, and we can read its story in the young seafloor and the torn mountains it left behind, then what came before it? What gathered world existed before Pangaea and broke before Pangaea so long ago that the very ocean floor that recorded its shattering has been completely destroyed, swallowed back into the depths of the earth, leaving no fresh trail at all? Because here is the thing about deep time, the thing that makes this whole story possible and almost impossible at once. The continents endure. The granite of the continents is old, almost unimaginably old. The oldest continental rock we have found, a formation called the Acasta gneiss in the far north of Canada, is something on the order of 4 billion years old, 4,000 million years. And tiny crystals, grains of a mineral called zircon recovered from a place called Jack Hills in Australia, are older still, reaching back something like 4.4 billion years, nearly to the very birth of the planet itself. The continents, remember, they carry rock from the dawn of the world. But the ocean floor forgets. The sea floor is young, shockingly young by comparison. Nowhere on Earth is there ocean floor older than about 180 to 200 million years. Think of that gulf. The oldest continental rock, 4 billion years. The oldest ocean floor, 200 million. The continents hold rock from nearly the beginning of time, while the oldest scrap of seafloor is younger than the breakup of Pangaea. The oceans are forever being born and forever being swallowed, made new at the cracks and destroyed at the edges, while the continents drift on above them, ancient and enduring, like rafts of old wood floating on a sea that is endlessly recycled beneath them. And that is the heart of the mystery. We will spend the rest of this long, slow night unraveling. The supercontinents before Pangaea broke apart so long ago that their oceans have been entirely destroyed, every scrap of that recording seafloor swallowed back into the deep earth. There is no fresh trail to follow. And yet we know those earlier worlds existed. We have rebuilt them, mapped them, given them names. We have reconstructed continents whose oceans no longer exist anywhere on the planet, gathered worlds older than the first animals, by reading the faintest of clues frozen into the enduring stone of the continents themselves, mountains torn into pieces, compasses frozen into cooling rock, the fingerprints of a single fern scattered across 5 continents, the scratch marks of ancient ice. These are the threads, and from them patient minds have woven back together worlds that vanished hundreds of millions, even billions of years ago. So let that be the promise I make you tonight, the one I will keep slowly, gently, across all the hours to come. We are going to descend together through deep time. We are going to walk backward through the gathered worlds, past Pangaea, into the ones before it, and the ones before those, fading into the oldest dark. We are going to learn how it is done, this rebuilding of vanished worlds, the strange and patient detective work that lets a person hold a piece of stone and read in it the latitude of a continent that no longer exists. We are going to find the engine, the deep, slow force that pulls the continents together and tears them apart, the reason the ground can never sit still. And at the very end, far from here, we are going to stand at the edge of the future and look at the next gathered world, the one assembling beneath our feet right now, the one that already has names. But all of that is for later. For now, there is no need to follow every thread, no need to hold on to every number or remember every name. They will return gently again and again. For now, it is enough to lie here and feel the slowness of it. The ground beneath you, moving at the speed your fingernails grow, and never once stopping. The thumb's width of new ocean opening every year. The 4 billion-year-old stone and the 200 million-year-old sea. Pangaea, all the land in one, with its desert heart and its breathing monsoon and its single-world ocean, broken now and scattered into the shapes you know, the latest verse of a song the planet has been singing since long before anyone could hear it. Breathe in slowly, feel how the breath rises the way an ocean rises into vapor and gathers into cloud, and breathe out slowly, the way the rain comes down, the way the continents drift, unhurried, patient, certain of their direction, even across 200 million years. There is nowhere you need to be. The mountains took their time, the oceans took their time, you may take yours. And as the dark settles in around you, let yourself begin to sink toward the deep, the way a grain of ancient zircon settles slowly toward the floor of a vanished sea, the way the whole solid world turns quietly beneath the stars without ever asking you to hold it up. The land is moving. It has always been moving. It will move long after this night, and the next, and the 1,000 nights after that. There is a strange and gentle comfort in that, if you let there be. Nothing here is truly still. Everything solid is, in its own unhurried way, traveling. And so are you, carried on the slow back of a continent, drifting through the dark at the speed of a growing fingernail, toward a morning that will arrive in its own time, and toward a gathered world that has not yet been born. For now there is only the slowness and the warmth and the long, deep breathing of the earth beneath you. Let it carry you. We have only just begun to descend, and there is so much more below. Welcome to Relaxing Wisdom. Tonight we are going somewhere very old and very large, and we are going there slowly, so let your shoulders fall, and let the bed take your weight, and let me lead. Consider that number again, gently, the way you might turn a smooth stone in your palm in the dark. 2 to 10 centimeters a year. That is how fast the ground moves, slower than a vine climbs a wall. About the speed your fingernails lengthen as you sleep. You will not feel it tonight, and you would not feel it across a whole long life, and yet it never rests. The Atlantic, the wide grey ocean between the old world and the new, grows wider by about 2 to 2.5 centimeters with every passing year. A hand's breadth in a human lifetime, thousands of kilometers across 200 million years. The water you might picture rolling onto a beach is sitting in a basin that is quietly, endlessly getting bigger, as if the world were drawing a long, slow breath and never quite letting it go. And here is the first strange thing, the thing that begins to open the door to the mystery. The floor of that ocean is young, astonishingly young when you set it beside the rest of the planet. The oldest ocean floor anywhere on Earth is only about 180 to 200 million years old. That is the very furthest back the seabed remembers. Older than that, and the record simply is not there because the floor has been swallowed, drawn back down into the deep and remade. The ocean is forever being born along its ridges and forever dying along its edges, a thin, dark crust that never gets to grow old. But the land. The land is another matter entirely. The land endures. In the far north of Canada there is a rock called the Acasta gneiss, and it is about 4 billion years old. Sit with that for a moment. 4,000 million years. And out in the dry hills of Western Australia, in a place called Jack Hills, there are tiny crystals, grains of zircon no bigger than a speck of sand, and some of them have been measured at roughly 4.4 billion years. They are older than almost anything else we can hold. They were already old when the oldest patch of seabed was not even a thought. So the continents are the keepers of deep time, and the oceans are forever young, forever being unmade. The land remembers what the sea forgets. Before we go further down, let me ask you something, softly. No need to do anything but let the question drift past. Wherever you are tonight, in whatever city or quiet room or far corner of the world, I find myself curious where you are listening from. If you feel like leaving a word in the comments before sleep takes you, I would like that. And if these slow journeys help you find your way to rest, you might subscribe so the next one finds you when you need it. That is all. Let it go now. We have a vanished world to descend into, and here is the promise I make you for the long night ahead. Pangaea, the great gathered land you may have heard named, the one supercontinent that floats in so many imaginations, is not the only one. It is not even the first. It is simply the latest verse of a song the planet has been singing for 2 billion years, and very nearly the only verse whose music still survives clearly enough to read. We are going to go down through that song slowly, layer by layer, into worlds whose oceans no longer exist, and we are going to see how anyone could possibly know they were ever there at all. But first, the clue. The vivid, picturable, almost unbelievable clue that cracks the whole thing open. Imagine you could lay 3 mountain ranges side by side on a table. The Appalachians, those long, worn green ridges that run down the eastern side of North America, soft now, rounded by unfathomable ages of rain. The Caledonides, the ancient bones of the Scottish Highlands and the spine of Scandinavia. And the Anti-Atlas of Morocco, rising out of the edge of the Sahara. 3 ranges, 3 continents, an ocean between them. And yet they are the same mountains. One single chain raised together when the land collided long ago and then torn into 3 pieces by an ocean that opened straight down the middle of them and pushed the fragments apart. The mountains of Scotland and the mountains of Morocco and the green hills of the American East are siblings, separated at birth and carried away from one another at the speed of a growing fingernail until a whole sea lay between what had once been a single wall of stone. That is the kind of clue that lets us rebuild a lost world. And the world it points back to is Pangaea. Picture it now as the dark closes softly around you. A single landmass gathered together between roughly 335 and 300 million years ago, all the wandering pieces of crust drawn slowly into one. It held together for a long, long while, and then, around 200 million years ago, in the early Jurassic, it began with infinite patience to come apart again. A man named Alfred Wegener gave it its name in 1912, Pangaea, all Earth, one word for the whole gathered world, and around it a single ocean, just one, wrapping the entire planet, a sea so vast it had no far shore that was not also its near shore, because it went all the way around. Panthalassa, the all-sea. Hold that picture soft and enormous in the dark, one land and one ocean encircling it, and reaching in from the east, curling into the side of the supercontinent like a great warm bay, another arm of water, the Tethys. So the map of that world was simple in a way our crowded modern map is not. A gathered land, a world ocean around it, a warm sea breathing into its eastern flank. And the heart of that land, far from any coast, was a desert. It could be no other way. When you gather all the continents into one enormous mass, the deep interior lies thousands of kilometers from the nearest shoreline, and the rain that the sea gives up simply cannot reach so far inland. So the middle of Pangaea was vast and dry, an arid continental heart on a scale the present Earth has nothing to match. And around its edges, where the land met the water, the climate swung hard between the seasons, great monsoon rains sweeping in and then withdrawing, a planet-sized breathing of wet and dry that geologists call the mega-monsoon, a breathing interior, a breathing climate, a world that inhaled the rains along its margins and exhaled them again, year after year, for 100 million years and more. That is the world we are standing at the edge of tonight. Already broken, already scattered into the familiar shapes you learned as a child, the coastlines you could trace from memory. But once, whole. And here is the thing that should settle over you now like a warm weight, the thing that turns one fact into a doorway. If Pangaea came together and then broke apart, then something came before it, some earlier gathering, some older world with its own oceans long since swallowed and gone, and before that perhaps another. The breaking of Pangaea is not the beginning of the story. It is the most recent ending in a story that goes down and further down still. So let yourself keep sinking gently with no effort at all, the way the land itself drifts without ever straining. We have named the latest verse. We have heard its single great ocean and felt its desert heart. And below it, in the deep dark of even older time, the song goes on. Let the wisdom settle soft, the rest will come on its own. But before we can descend into those older worlds, we have to answer a question that ought to stop you cold. How do we know any of this? Pangaea is 200 million years gone, Its ocean, Pangaea, has been entirely swallowed into the mantle. There is no photograph, no satellite image, no written record. The creature that would eventually become the first human would not arrive for another 199 million years or so after Pangaea began to break. So when a geologist draws a map of that vanished world, when they sketch the outline of Gondwana pressed against Laurasia, the Tethys curving between them like a crescent sea, and they say with quiet confidence that this is how it looked, how exactly do they know? The answer is one of the strangest and most beautiful stories in all of science. It is a story about frozen compasses, about mountains that remember which hillside they once pressed against, about tiny crystals carrying clocks inside them, about a fern whose dead leaves spoke across 5 oceans, and about a man who was right about everything and ignored until he was dead. And it matters to understand this story because the further back we go, the older the supercontinents we are trying to find, the more completely we depend on these methods. Pangaea we can reconstruct with something approaching confidence. Rodinia, older by 600 million years, comes to us through fog. The worlds before it are little more than whispers. Understanding how the detective work is done is what lets you understand why some of these ancient maps are drawn with a firm line and others with a trembling, uncertain hand. Begin with the rock itself. When lava erupts from a volcano and begins to cool, there is a brief window, as the mineral crystals are still forming and the liquid is becoming solid, during which small magnetic minerals inside the cooling rock, magnetite above all, behave like tiny compass needles. They align themselves to Earth's magnetic field, the same field that guides a compass on your bedside table, the field whose lines run from magnetic pole to magnetic pole, looping through the planet and out into the sky above. And as those minerals crystallize and lock into place, they carry that alignment with them, permanently, forever. Unless the rock is later heated past a critical temperature called the Curie point, which would wipe the record clean the way strong heat can demagnetize an old compass needle. Short of that, the minerals hold their position across millions and billions of years, patient beyond imagination, pointing still toward where the magnetic pole stood on the day the rock solidified. This is paleomagnetism, and what it gives a geologist reading those frozen alignments in a rock of known age is the latitude of the place where the rock formed, not longitude, which we will come to in a moment, and not the absolute direction of north, which has shifted over time as the poles wandered, but latitude expressed through the angle of the magnetic field lines, which run nearly horizontal at the equator and plunge steeply downward as you move toward the poles. This angle, called the magnetic inclination, is built into the frozen compass like a spirit level. A volcanic rock that formed at the equator will have near horizontal magnetic mineral alignments. One that formed near a pole will have alignments pointing sharply down into the earth. Measure the inclination and you can read the latitude where the rock was born. In practice, the work is painstaking. Geologists take oriented core samples from outcrops, careful to note the exact direction each sample faces in the field before it comes loose from the hillside. Then in the laboratory, they drill small cylinders from those cores, measure the direction and inclination of the magnetic signal in each one, and after correcting for the local tilt and deformation the rock may have suffered over millions of years, they arrive at a paleolatitude. Trond Torsvik and his collaborator L. Robin Cox, who together produced one of the most comprehensive atlases of Earth's ancient geography, have spent careers assembling these readings from rocks on every continent, building a database of past positions that spans much of Earth's history. From this database, you can watch the continents drift across ancient latitudes like slow ships across a patient sea. But here is the catch that took decades to fully appreciate. Paleomagnetism gives you latitude. It does not give you longitude. And the reason is quietly devastating if you think about it for a moment. Earth's magnetic field is symmetrical around the planet's spin axis. A rock sitting on the equator in what is now Brazil, reads a certain inclination. A rock that formed on the equator in what is now Central Africa at the very same moment in deep time reads the same inclination. You cannot tell from the magnetic signature alone whether the rock was east or west of anywhere else. The field makes no distinction. You can pin a continent to its ancient latitude with some confidence, but you cannot pin it to its ancient position along that latitude without additional evidence. Think of it as knowing which rung of a ladder you stood on without knowing which part of the room the ladder was leaning against. This longitude blindness is why the maps of Rodinia, the supercontinent older than Pangaea by hundreds of millions of years, look so different depending on which research team drew them. If you were to set 5 published reconstructions of Rodinia side by side, you would find that the continents they include are roughly the same, that the researchers broadly agree on which ancient landmasses were involved, but their relative positions along east-west lines vary considerably from one map to another. The edges can be anchored. The interior arrangement remains, in the honest language of the science, genuinely uncertain. Geologists work around the longitude problem by gathering every scrap of additional evidence they can find, matching rock formations that must once have been continuous, ancient rifts whose geometry constrains how far apart 2 blocks could have been, sedimentary basins that only make sense if 2 pieces of crust were neighbors. Each constraint narrows the range of possible positions, but it can rarely fix longitude with the precision that paleomagnetism fixes latitude. The fog does not fully lift, and there are limits even within what paleomagnetism can do well. The older the rock, the more likely it is that subsequent heating or deformation has partially overprinted the original signal, the way a photographic negative slowly fades if left too long in a bright room. Separating the original ancient signal from later overprinting requires careful lab technique, specialized equipment that gradually demagnetizes the sample in steps, watching to see at what temperature or field strength the original alignment surfaces from beneath the later noise. Even then, certainty decreases the further back you go. The record from the last 500 million years is reasonably good. The record from 1 billion years ago is patchier. The record from 2 billion years ago is fragmentary, read-through rock that has been folded, heated, and reworked more times than anyone can count with confidence. So paleomagnetism is the most powerful single tool for deep time reconstruction, and also a tool with built-in limits that every careful researcher acknowledges openly. That honesty is part of what distinguishes the science from the story. The maps we make of ancient supercontinents are not assertions of certainty. They are best estimates, bounded by evidence, with regions of genuine unknown where the lines are drawn lightly. Now set paleomagnetism aside for a moment and consider a very different kind of evidence. One that does not read electromagnetic signals at all, but instead reads the shape of the land itself. When 2 continents collide, driven together by the closing of an ocean between them, the rock at the collision zone crumples and is thrust upward. Mountains form. Not from any volcanic drama, but from the simple, titanic compression of 2 continent-scale rafts of crust meeting face to face, neither willing to go under, both piling up at the seam. The Himalayas today are rising this way as India, which broke from Gondwana and travelled north across what had been the Tethys Ocean, rams steadily into Asia. The Alps rose when Africa nudged into Europe. The Appalachians, when you look at them today, are old and worn, their peaks rounded by 200 million years of rain and ice, their highest points barely a third the height of the Himalayan giants. But they were not always modest. When they formed, during the great collision that assembled Pangaea, they may have rivaled anything the present world has standing. And here is what makes mountains so useful to the detective. When a supercontinent later breaks apart, the rifts do not always tear neatly through flat, featureless ground. They tear through whatever landscape exists, which includes those old mountain belts, and they leave pieces of those mountains on different continental fragments that then drift apart. The mountain range is torn like a page torn from a book. Each piece still bears the same text, the same rock types, the same structural style, the same sequence of formations, the same fossils, the same deformation history, but now separated by an ocean that opened in the gap left by the tear. To match them back up is to reconstruct, at least locally, where the two pieces once pressed together. The Appalachian Mountains of eastern North America, running from Alabama up through the New England states and into Canada, are a torn fragment. Their other pieces lie across the Atlantic. The Caledonides, the ancient crumpled spine of Scotland and Scandinavia, running up through the Scottish Highlands and northward into Norway and on into Greenland, carry the same story in their rocks. Same ages of formation, same sequence of rock types, same kind of folding and thrusting, the fingerprints of the same ancient collision. And further south, across a wider stretch of ocean, the mountains of Morocco, the anti-Atlas, bear related signatures from the same event. Once, these were not three separate ranges on three separate land masses. They were one continuous mountain chain, a great welt of crumpled crust running from what is now North Africa up through what is now Europe and across into eastern North America. The ocean that opened between them, filling in as Pangaea broke apart, separated what had been continuous. Now read the fragments and you reconstruct the seam. Geologists call these matching points across rifted continents piercing points. A piercing point is any geological feature, a rock formation, a fault line, a distinctive intrusion of igneous rock that can be traced continuously on one side of a former rift and matched unambiguously to its continuation on the other side. A well-constrained piercing point is a geometric anchor. It tells you not only that two pieces were once joined, but exactly how they fit together, like finding the matching edges of two torn pieces of a letter and confirming which word ran across the tear. The more piercing points you can establish between two continental fragments, the more tightly you can constrain how they fit before they separated. A related technique looks not at the shapes of rocks but at their ages, and it depends on a tiny crystal you could hold many of on your thumbnail. Zircon is a mineral that forms in igneous rocks, particularly in the granites, that make up much of continental crust. It is extraordinarily resistant to chemical breakdown, which is why zircon grains survive for billions of years, even as the rocks around them are weathered away, and the sediment is carried off by rivers and deposited somewhere else as sandstone or mudstone. Those grains are called detrital zircons, zircons that have been eroded from their original source and deposited far downstream, carrying their age with them. And the age is readable precisely because zircon incorporates uranium into its crystal structure when it forms, but refuses to accept lead. So as the uranium decays into lead over time, the ratio of uranium to lead in a zircon grain tells you with high precision how old that grain is. This is uranium-lead dating, and it is one of the most reliable clocks in geology. Now imagine you are looking at a sandstone in what is now Western Africa. You extract the detrital zircon grains from it and measure their ages. You find a cluster of grains around 1.8 billion years old, another cluster around 2.7 billion years old, another around 1.0 billion years old. These clusters are not random. They record the ages of the source rocks, the ancient mountains that were being eroded at the time that sandstone was deposited, the mountain ranges that fed sediment into whatever river or coastal system laid down those grains. Now you look at a sandstone in what is now South America. You find the same clusters of ages, 1.8 billion, 2.7 billion, 1.0 billion. The probability of two widely separated continents independently producing identical combinations of ancient source ages is effectively nil. The only explanation is that they were sharing the same mountain ranges because those mountain ranges stood between them and erosion filled the basins on both sides with material from the same source. They were neighbors. They were part of the same world. This detrital zircon fingerprinting, as it is sometimes called, has become one of the most powerful tools for linking ancient continental fragments and rebuilding lost supercontinents. It works even when the original mountains have been completely eroded away, leaving no visible structure at the surface. The grains still carry the memory of those mountains inside them, patient little clocks sealed in ancient sand, waiting for someone to read them. But not all the evidence requires a laboratory. Some of it walks into the story on its own, written in shapes that any careful observer can recognize. Consider a plant called Glossopteris. It was a seed fern, extinct now, and it lived during the Permian period, roughly 250 to 300 million years ago, in the wet coastal margins and swampy lowlands of the southern supercontinent geologists call Gondwana, which at that time was the southern portion of Pangaea. Glossopteris had long, tongue-shaped leaves with a distinctive central vein, and it grew abundantly wherever the conditions suited it. Its fossils appear today in the rocks of South America, Southern Africa, India, Antarctica, and Australia. 5 land masses now separated by wide ocean spread across a quarter of the globe's surface, and all of them carry the same plant. Glossopteris could not cross open ocean. It was a land plant, rooted in soil, dependent on insect and wind pollination, producing seeds that fell to earth and germinated nearby. It could no more have colonized 5 continents separated by thousands of kilometers of ocean than an oak tree could walk across a lake. The only explanation for its presence on all 5 landmasses is that those landmasses were once connected into a single continuous territory where the plant could spread by ordinary, slow, terrestrial means. Seeds carried a few kilometers each generation, populations spreading over millennia, the way a forest advances into cleared land after a fire. Its fossil leaves are not just botanical curiosities, they are maps. They draw the outline of Gondwana in pale green, pressed into rock. Alongside Glossopteris, another creature makes the case even more precisely. Mesosaurus was a small reptile, perhaps a meter in length, that lived in fresh water during the early Permian, around 270 million years ago. It had long jaws filled with fine teeth, probably suited to straining small animals from the water. A freshwater animal cannot cross an ocean. Salt water would kill it. And yet Mesosaurus fossils are found in only 2 places on Earth, in rocks of South America and in rocks of Southern Africa. Nowhere else, not in North America, not in Europe, not in Asia, not in Australia. Only in those 2 places on opposite sides of the South Atlantic Ocean. The South Atlantic did not exist when Mesosaurus was alive. There was no ocean to cross. The animals lived on what was then a single piece of land, in freshwater lakes and rivers that stretched from what is now Brazil to what is now Cape Town, on a continent that would not begin to split apart for another 50 or 60 million years. Their fossils, locked into the sedimentary rock of that single ancient landscape, were then carried apart on the separating fragments of that rock as the Atlantic opened, like 2 halves of a pressed flower torn slowly apart along the spine of the book. Alfred Wegener used Glossopteris and Mesosaurus, among other fossils, when he proposed continental drift in 1912 and laid it out in his book in 1915. He was a meteorologist, not a geologist, and that background both helped and hindered him. It helped because he came to the problem without the professional geologist's training to see oceans as permanent fixtures of the landscape. It hindered because when the geologists of his time challenged him to name the force that could move something as massive as a continent through solid oceanic rock, he could not give them a satisfying answer. He proposed variously that the continents were pushed by centrifugal force from the rotation of the Earth or by tidal forces from the Moon. Both proposals were quickly shown to be far too weak to do what he claimed. The mechanism was not there, and without a mechanism, the evidence, however suggestive, could not carry the day. The geological establishment of the early 20th century looked at his maps and his fossils and his matching coastlines and said, coincidence, or more charitably, interesting but unexplained, and went on teaching that the continents were fixed. Wegener continued working on the problem and on other areas of science, but he never saw vindication. He died in Greenland in 1930 during an expedition on the ice sheet that had consumed so much of his attention alongside the drifting lands. He was 50 years old. His hypothesis drifted on without him, rejected or ignored by most of the scientific community for another 30 years. Then the seafloor began to speak. In the years after the Second World War, oceanographic research expanded dramatically, partly driven by military interest in knowing the ocean floor for submarine navigation, and partly by new instruments and techniques that made deep-sea mapping possible at scale. What the surveys revealed was startling. The ocean floor was not the flat, featureless plain people had assumed. It had a topography as dramatic as anything on land, including a vast ridge system running down the center of the Atlantic Ocean like the spine of a serpent, thousands of kilometers long, rising several kilometers from the abyssal plain. And the rocks on either side of this mid-ocean ridge were young. Not just young by geological standards, young by almost any standard. The youngest rock was at the ridge itself. Moving away from the ridge in either direction, the rocks grew progressively older. The ocean floor was spreading away from the ridge, new rock being created at the center and moving outward. Harry Hess, an American geologist, laid this out in 1962 in a paper he called, with characteristic modesty, an essay in geopoetry. He described the ocean floors as giant conveyor belts continuously created at the mid-ocean ridges and continuously destroyed at the ocean margins, where they dove back beneath the continents. The mechanism Wegener had lacked. The continents did not plow through the oceanic rock. They rode on top of it, passengers on the spreading seafloor, pushed and pulled by the same process that was continuously generating new ocean floor and consuming old. The continents moved because the plates they sat on moved, and the plates moved because of what was happening at their edges. But Hess had written poetry. What turned poetry into proof arrived a year later from two British researchers named Fred Vine and Drummond Matthews. They were studying the magnetic properties of the ocean floor near a mid-ocean ridge in the Indian Ocean, and what they found was a pattern. The ocean floor was magnetized in alternating stripes, a band of rock with a magnetic field oriented in the normal direction, as today, then a band with the field reversed, then normal again, then reversed, the stripes running parallel to the ridge axis and mirrored symmetrically on both sides. It was, when you stepped back from it, a barcode of the Earth's magnetic field as it had been, recorded in the rock of the ocean floor at the moment each stripe cooled and froze. Earth's magnetic field is not stable over geological time. It flips, irregularly but repeatedly, with the north and south magnetic poles trading places on timescales of tens of thousands to hundreds of thousands of years. When a new stripe of ocean floor cools at a mid-ocean ridge, the magnetic minerals in the basalt freeze the orientation of the field as it is at that moment, whether normal or reversed. As the seafloor spreads outward from the ridge over millions of years, each successive stripe records the field polarity at the time of its formation. The result is a continuous magnetic diary of the ocean floor's creation, written in alternating bands and mirrored on both sides of the ridge because the seafloor spreads in both directions simultaneously. Vine and Matthews published their analysis in 1963 in the journal Nature. They showed that the stripe pattern matched, in its timing and spacing, the known chronology of geomagnetic reversals measured independently from cores of volcanic rock on land. The ocean floor was not just spreading, it was a tape recorder, and the tape matched. With that, continental drift, now understood as plate tectonics, became essentially incontrovertible. The mechanism was real. The ocean floor was being created and destroyed in a grand global cycle. The continents had moved, were moving, would continue to move. Wegener had been right. Not about the mechanism, which he got wrong, but about the fundamental fact. The continents had been assembled, and they had come apart. Alexander du Toit, a South African geologist who had been one of Wegener's few early defenders, had argued in his 1937 book that the southern continents told a coherent story of assembly and separation, and had laid out the glacial and fossil evidence with great care. He had largely been ignored too. Now, his evidence was reread in a framework that made sense of it. Those glacial striations that du Toit had catalogued deserve a moment of attention because they are perhaps the most visceral and immediate piece of evidence for the Gondwana assembly. During the Permo-Carboniferous period, roughly 300 million years ago, a vast ice sheet covered much of the southern portion of Pangaea. As glaciers move, they carry embedded stones and grit that grind against the underlying bedrock, leaving long parallel scratches in the rock surface called striations. Those scratch marks record the direction the ice was moving at the time it passed. If you find a surface of ancient bedrock with Permo-Carboniferous striations on it, the scratches tell you which way the ice traveled across that spot. Now here is the puzzle that disturbed geologists long before anyone proposed continental drift. Those glacial striations appear on outcrops across South America, Southern Africa, Peninsular India, Antarctica, and Australia. And in several places, the scratches point toward what is now open ocean, not just toward the coast, but out to sea, as if the ice that made them came from a direction where there is now nothing but water, no landmass, nothing for thousands of kilometers. If you treat those 5 landmasses as they are now, scattered across the southern hemisphere, the ice sheet that left those marks would have had to be impossibly configured, sometimes flowing uphill against the ocean, and sometimes radiating from a center located in the middle of the sea. It makes no sense as a picture of today's geography. But if you close the Southern Ocean, if you slide South America back against Africa, press Africa against Antarctica, fit India up against the eastern margin of Antarctica, and lock Australia against Antarctica's other side, and assemble all 5 into the single continuous supercontinent of Gondwana, something remarkable happens to those scratches. They suddenly point coherently inward toward a single central source. The ice flowed outward from a highland at the heart of Gondwana, covering what is now Antarctica, spreading radially across the surrounding lowlands. The scratch marks, which look nonsensical, spread across today's ocean-divided world, become a perfectly sensible radial flow pattern when the continents are reassembled. The ice itself, absent for 300 million years, wrote its directions into the rock, and the rock remembered. This is the quality of evidence that, when you sit with it slowly in the dark, has a particular kind of weight. It is not an argument. It is not a model or a simulation or a theoretical prediction. It is a scratch on a stone that points in a direction. And that direction, that physical, permanent, unambiguous direction, scratched into bedrock by ice that no longer exists, only makes sense if the world was built differently than it is today. The stone does not care about the theory. The stone just points. By the mid-20th century then, and accelerating after Vine and Matthews in 1963, the evidence from paleomagnetism, from matching mountain belts, from detrital zircon ages, from fossils that could not swim, and from scratch marks on ancient floors that pointed toward vanished ice sheets, had come together into something close to a consensus. The continents had been joined, Gondwana in the south, Laurasia in the north, together making Pangaea. Pangaea had been whole, and it had broken. The ocean that opened between South America and Africa, between Europe and North America, was a young ocean. Old by human measure, but young by the measure of the planet. The floor of the North Atlantic is not even 200 million years old in its oldest parts, and in the South Atlantic it is younger still. The ocean is new, the continents on either side are ancient, the separation is geologically recent. But this was, in a way, still only the surface of the story. It answered the question of Pangaea. It did not yet answer the question that Pangaea itself opened. What came before? And that question is the one that takes you down into genuine darkness, because when Pangaea broke, the ocean floor that records the geometry of that breakup, the magnetic stripes, the spreading ridges, all of it still exists in fragments. You can still find pieces of those original ocean floors and read them. But when Rodinia broke apart, 600 million years before that, the ocean floor it created was subducted, swallowed back into the mantle, every magnetic stripe, every sedimentary record from those vanished ocean basins destroyed. To reconstruct Rodinia and the supercontinents older still, you have only the continents themselves to work with, and whatever those continents chose to preserve. And this is why the detective methods matter so intensely for the deeper past. For Rodinia, there are no magnetic stripes to read because the ocean floor is gone. There are only the ancient magnetized rocks of the continents themselves, which record paleolatitude but not longitude, and which grow patchier and more overprinted the older they are. There are the torn mountain belts whose fragments can sometimes be matched across continents now separated by oceans that opened long after the original collision. There are the detrital zircon grains whose age populations can link continental fragments that once shared mountain ranges. There are the ancient rift zones within continents, recording where the land once began to pull apart, and sometimes marking the ghost of an older ocean that once existed and was later closed. And there is the geometry of the ancient orogenic belts, the great zones of compression and deformation left by ancient mountain-building events, which record where continents once collided even after the mountains themselves have eroded entirely away. From these clues, incomplete and sometimes contradictory, geologists have assembled a reconstruction of Rodinia, not a single agreed reconstruction, but a family of reconstructions, differing in their details, each defensible within the limits of the available evidence, none certain. The major pieces of the puzzle, the large ancient continental cores called cratons, the stable, geologically ancient hearts of continents, can be placed roughly. Where exactly they sat relative to one another, east and west of each other, remains in some cases genuinely disputed. The longitude blind spot is widest here, in the oldest chapters of the story, where the evidence is thinnest. This is not a failure of the science, it is an honest account of what the evidence permits and what it does not. A reconstruction of Rodinia drawn with false confidence, with all the continents neatly arranged and labelled as if the answer were settled, would be more misleading than a map that shows the uncertainty explicitly, with dotted lines where the evidence is weak and solid lines only where the constraints are genuinely tight. The best researchers in the field draw the dotted lines. They write the hedges into their papers. They say, "This is our best estimate, and here is how confident we are in each part of it." That habit of calibrated honesty is what distinguishes science from storytelling, even when the story it tells is true. And so this is how we know what we know, and this is why we know it only to the degree that we do. The frozen compass needles in ancient volcanic rock, reading off latitudes that held in place while the rock itself moved halfway around the world. The torn-apart mountain ranges still wearing their shared geological ancestry in their deformed rock like a family resemblance across generations. The tiny zircon crystals, smaller than grains of table salt, each carrying a uranium-lead clock that has been ticking since the moment the crystal formed in cooling magma 1 billion or 2 billion years ago, waiting for a geochemist to open it. The fossil leaves of Glossopteris pressed flat in shale, telling a story of a southern world that was whole. The fossil bones of Mesosaurus, a creature that lived in freshwater rivers on a continent that no longer exists as a single entity. The striations on ancient bedrock pointing silently toward ice that melted before the dinosaurs existed, toward a center that is now dispersed across 5 continents and an ocean. Each line of evidence is partial, each has its limitations, its blind spots, its zones where the signal fades or the interpretation is contested, but together they triangulate on a truth that is genuinely knowable to a degree that would have seemed impossible 100 years ago. We know that the continents were once assembled. We can date when they assembled and when they began to break. We can say, with confidence proportional to the quality of the surviving evidence, where the major pieces were relative to each other and how the ocean basins between them opened and closed. We can trace the shape of vanished mountain chains through the fragments they left on departing continents. We can identify the ancient ocean floors now vanished by the suture zones they left behind when the oceans that held them were consumed, the compressed and metamorphosed slivers of ocean crust occasionally scraped off the subducting plate and plastered against the overriding continent as a geological scar called an ophiolite, a piece of ancient sea floor stranded on dry land, telling you an ocean once stood here. The story of how we learn to read these signs is inseparable from the story of the supercontinents themselves. Wegener, dying on the ice, unvindicated, is part of the story. Vine and Matthews reading the barcode on the ocean floor and recognizing it for what it was are part of the story. Du Toit, the careful South African who catalogued the scratch marks and the fossils with great precision and was largely ignored, is part of the story. The story of science is rarely a smooth, straight road. It is a road that doubles back, that crosses disputed territory, that loses its way in apparently empty wilderness for decades before someone finds the trail again. But the trail was always there. The evidence was always frozen in the rock, waiting. It did not care how long it waited. It had, after all, been waiting for millions and millions of years already. A few decades more made no difference to the stone. And what the stone ultimately shows through all these methods working together, through the paleomagnetism and the matching rock belts and the zircon clocks and the fossil ferns and the glacial scratches and the magnetic stripes on the ocean floor, is something larger than any one supercontinent. It shows the cycle, not just that Pangaea existed and broke, but that something before Pangaea existed and broke. And before that, another. The breakup of Pangaea was not the first time the planet shattered a unified landmass into a set of wandering fragments. It was, as best we can tell, at least the 3rd or 4th time, perhaps more. The continents have been gathering and separating since long before any of the evidence we can currently read, in a rhythm so slow it makes the lifespan of a mountain seem like a breath held and released. So there is a cycle, a great turning, a planetary rhythm in which the continents gather and then scatter, oceans open and then close, the world assembles itself into a single face and then shatters that face and rebuilds it again. That rhythm is what the next part of this journey will follow, down through the names and ages of the worlds that came before Pangaea, down through Rodinia and Nuna, and the older, more uncertain shapes that preceded them, and down into the engine at the planet's heart that keeps the rhythm going, because the cycle does not run on nothing. Something drives it. Something deep and vast and still poorly understood keeps the continents moving, keeps the plates in motion, keeps the whole slow machinery turning. And understanding what that engine is and how it has run for more than 2 billion years without stopping is the next place this quiet night will take you. The name Rodinia comes from a Russian word, not a Latin root, not a Greek stem, but the Russian verb rodit, to give birth, to beget. Mark and Diane McMenamin chose it in 1990, and the choice was not arbitrary. This was the supercontinent that, when it broke apart, begat the conditions for something that had never existed before on Earth. But we will arrive at that consequence in its own time. First, the shape of the world itself, as best we can reconstruct it, roughly 1 billion years ago, when Rodinia was whole. Rodinia assembled, as near as geologists can determine, somewhere between 1.3 and 0.9 billion years ago. Think of that as a range of roughly 400 million years, during which fragments of continental crust, some ancient even then, some of them carrying rock that was already 2 or 3 billion years old before Rodinia even began to form, were gradually drawn together by subduction, by the closing of oceans whose names we do not know and whose floors were long ago recycled back into the mantle without leaving a trace at the surface. By the time that assembly was complete, perhaps around 900 million years ago, most of the Earth's continental crust was gathered into a single body. One world. Again. And then it came apart. Beginning roughly 750 million years ago, Rodinia began to fragment, and by around 630 million years ago, the breakup was well advanced. The continents that had been held together drifted outward, separated by new oceans, scattered across latitudes they had not occupied before. And in that dispersal, something extraordinary happened to the planet. Something that will take its proper place in the telling soon enough, but whose shadow we should acknowledge even now. The world nearly froze solid. The breaking of Rodinia and the onset of the snowball Earth glaciations are events that sit close together in deep time, close enough that they are almost certainly connected. But the mechanism of that connection and the strange flowering of life that followed the thaw belongs to a later movement of this night's journey. For now, consider what it means to say that Rodinia existed. It means that the dance has been going longer than Pangaea, longer than anything visible in the ordinary landscape of the continents as we find them today. When Pangaea assembled, it was assembling pieces that had already been through at least one prior cycle of gathering and scattering. The rocks that made up Pangaea carried in their bodies the compressed scars of mountain belts formed when Rodinia's fragments collided, ancient fold and thrust belts long since worn to their roots, their original height unknowable, their chemistry still legible if you know how to read it. Pangaea was built partly from the rubble of Rodinia, and Rodinia was built partly from the rubble of what came before. The reconstruction of Rodinia is, by any measure, one of the most difficult intellectual exercises in the whole of geology. It sits at the edge of what the surviving evidence can support. Unlike Pangaea, whose ocean floors still partly exist, and whose breakup we can trace in seafloor spreading records and magnetic stripes, Rodinia's ocean floors are entirely gone. Every ocean that surrounded Rodinia, every basin that opened as it fragmented, and every basin that closed as it assembled, has been consumed by subduction. There is no seafloor barcode to read, no preserved oceanic crust carrying its magnetic signature. All that remains are the continents themselves, and the frozen compasses inside their rocks. Paleomagnetism, the reading of ancient magnetic orientations locked into cooling lava and settling sediment, is the most powerful single tool available for reconstructing a world this old. But as the previous movement of this story established, paleomagnetism gives you latitude and not longitude. It tells you how far north or south of the equator a piece of continent was sitting when a given rock formed, by measuring the inclination of the magnetic minerals, the angle at which the tiny crystals of magnetite aligned themselves relative to Earth's field. Near the equator, that angle is shallow, nearly horizontal. Near the poles, it tips steeply downward, as though pulled by the planet itself. The rock remembers the angle. Geologists measure it. From the measurement, they can recover the ancient latitude of the continent with reasonable confidence especially for rocks younger than about 1 billion years and better preserved. But the longitude remains invisible. Earth's magnetic field, on geological timescales, is symmetric around the spin axis. It doesn't matter whether you're standing in what is now eastern Canada or central China. If you're at 40 degrees north latitude, your magnetic inclination will be the same. The field gives no east-west signal, and this means that even with perfect paleomagnetic data from every fragment of Rodinia, even if every reading were clean and unambiguous, you could place each continent on its ancient circle of latitude and then slide it anywhere along that circle, east or west, without violating a single measurement. The east-west position is unconstrained. It must be inferred from other evidence, matching rock belts, matching zircon age populations, piecing together the geometry of which fragments could have been neighbors based on who their mountain belts suggest they collided with. And because this secondary evidence is incomplete, imperfect, and variously interpreted, different teams of researchers produce different maps of Rodinia. The exact arrangement of continents within it, which fragment was where, which coast faced which, is genuinely, honestly, uncertain. The shape of Rodinia is not a single agreed image. It is a family of overlapping proposals, each defensible within the limits of the data, each carrying its own uncertainties. This is not a failure of science. It is science working at its actual frontier, where the evidence is real and the conclusions are provisional, and honest researchers disagree. And it is one of the most quietly fascinating aspects of this whole field, that the world can be partially recovered from rock chemistry and frozen magnetism and zircon clocks, but that the recovery is never complete, that there is always a longitude problem, that the deep past is genuinely, irreducibly, partly unknown. The strangeness is not in the mystery being invented. The strangeness is in how much can be known and in the precise defined shape of what cannot. Beneath Rodinia, further down through the long darkness of Precambrian time, comes Nuna. This older supercontinent is also known by another name, Columbia, a name proposed by John Rogers and M. Santosh in a 2002 paper in Gondwana Research. Paul Hoffman had used the name Nuna earlier, tying it to the idea of a supercontinent built around what is now the northern continents, the ancient cores of North America, Europe, and parts of Asia. The name Columbia was attached to a more specific reconstruction, an attempt to pin down the geometry based on rock correlations and paleomagnetic readings. The two names, Nuna and Columbia, are often used interchangeably now, though some researchers prefer one over the other, and the fact that two names exist for the same proposed body is itself a small sign of the ongoing disagreement about its exact nature and configuration. Nuna assembled by current estimates somewhere between 1.8 and 1.6 billion years ago. Its fragmentation began around 1.5 to 1.3 billion years ago. It is older than Rodinia by somewhere between 400 and 700 million years, a span that is itself longer than the time separating us from the Cambrian explosion, from the first hard-bodied animals. Older by a vastness that the mind resists. What can be said of Nuna? Less than of Rodinia, and far less than of Pangaea. The rocks that carry its signature are fewer, more altered by the immense pressures and temperatures they have endured in the intervening time, more disrupted by later events. The paleomagnetic readings are noisier. The matching rock belts are harder to identify with confidence because so many later tectonic events have overprinted them. But the core of the evidence is there. Certain formations of rock in North America correlate in age and chemistry with formations in Northern Europe and with fragments in what is now India and Australia and parts of Africa, in ways that suggest they were once much closer, once part of a single body that has since been torn and scattered and partially reassembled into later configurations. One thing about Nuna that emerges clearly even through the noise, it was built around the nucleus of what geologists call Laurentia, the ancient craton that forms the heart of North America. Laurentia is very old. The rocks at its edges, the Acasta gneiss of Canada's Northwest Territories, have been dated to around 4 billion years, among the oldest intact rock formations on Earth's surface. The Jack Hills zircon grains from Western Australia, which are individual crystals and not an intact formation, carry dates of around 4.4 billion years, nearly as old as the planet itself. These fragments of the deep past, these survivors, were already ancient when Nuna assembled around them. They have been through everything. They have been at the core of one supercontinent after another, carried along as passenger rock, as ballast, as the stable, light, granitic foundation that endures while the oceans around it are born and swallowed. And then, even beneath Nuna, the evidence begins to thin and blur. There are names for older proposed supercontinents. Kenorland, thought to have formed around 2.7 billion years ago in the late Archean eon. Suggested to be around 3 billion years old, though some estimates push it younger. And Vaalbara, the oldest of the named proposals, with some estimates reaching back to 3.6 billion years ago, though with substantial uncertainty. These names exist. These proposals are real scientific hypotheses backed by real evidence, but the confidence one can place in them decreases steadily as the age increases. The further back in time a supercontinent is proposed, the less surviving crust there is to carry its signature. The more that signature has been overprinted by later events, and the harder it is to distinguish a genuine supercontinent from a large regional agglomeration that was never truly global in scale. Vaalbara is the most speculative of the named candidates, and honest accounts of it should carry that caveat clearly. The evidence for it? Correlations between certain rock formations in what is now Southern Africa and Western Australia is real, but whether those correlations indicate a supercontinent or something smaller and more local is a question that has not been settled. Kenorland is somewhat better supported, its evidence coming from the paleomagnetic record of the late Archean and from correlations of rock-forming events across what are now widely separated cratons. But even Kenorland is far from the certainty of Pangaea, or the reasonable confidence of Rodinia, or the moderate confidence of Nuna. Each step further back in time is a step toward greater uncertainty, toward a world in which the evidence is thin and fragmentary, and the honest answer to most specific questions is, we don't know yet. This is not discouraging. It is, in its own way, one of the most extraordinary things about this field of science. That from the light grain-sized crystals of zircon and from the alignment of magnetite particles, smaller than dust, from the angles of ancient mountain roots and the chemistry of sedimentary sequences, it is possible to see back 2.5, 3, even 3.5 billion years and propose, with some reasonable ground for the proposal, that the continents were doing then something like what they are doing now. The cycle, as best the evidence suggests, is not a recent phenomenon. It is as old as the planet's active tectonic life. Between Rodinia and Pangaea, there is one more figure in this story worth naming, though it must be named with care: Pangaea. This proposed supercontinent would have existed roughly between 630 and 570 million years ago, bridging the interval between Rodinia's fragmentation and Pangaea's assembly. The idea is that the fragments of Rodinia didn't simply wander independently until they gathered again, as Pangaea, but that some of them reassembled briefly into a second, shorter-lived supercontinent before dispersing again and ultimately rejoining in the Pangaea configuration. Some researchers accept Pangaea as a real, if brief, supercontinent. Others argue that the evidence for a full global assembly in that time window is insufficient, that what existed was more of a large southern agglomeration, a precursor to what would become Gondwana, without the global scope that the name Supercontinent implies. The debate is genuine and ongoing, and the honest position is that Pangaea is a contested hypothesis rather than a confirmed world. It may have existed. It may have been only partial. The evidence has not yet resolved it. What the evidence has resolved with something approaching full confidence is the cycle itself. The pattern that repeats, the rhythm that persists, the gathering and scattering that has been happening for at least 2 billion years and quite possibly longer. Pangaea assembles and breaks, Rodinia assembles and breaks, Nuna assembles and breaks. And the question that carries all the rest of the explanation on its back is, why? What drives this? What keeps the plates in motion? What is the engine that has been running without pause for so long? The answer has several parts, and the most important of them was not understood until the second half of the 20th century. In fact, it was not even suspected in its true form until the ocean floor began to give up its secrets. Imagine for a moment that you are standing on a mid-ocean ridge, which is one of the great submarine mountain chains that wind around the planet like the seam on a tennis ball, 60,000 kilometers of ridge in all, submerged beneath several kilometers of water. You cannot see it, but it is there, spreading. Along this ridge, hot rock wells up from the mantle and cools at the seafloor, hardening into new oceanic crust, basaltic and dark. And as it cools, it moves. The plate on either side of the ridge carries the new crust away from the spreading center, one plate moving left, one moving right, the ocean widening by centimeters each year. The Atlantic Ocean is widening right now by roughly 2 to 2.5 centimeters per year, the width of your thumb every year, year after year, which over 200 million years has opened an ocean thousands of kilometers across. But the ridge pushes with relatively modest force. The ridge push on the gravitational pressure of elevated hot rock at the spreading center was long thought to be the main driver of plate motion, and for a time it seemed like enough of an explanation. It is not. The real driver, the dominant force, is at the other end of the plate, where oceanic crust is old and cold and far from the ridge where it formed. It is dense. Basalt is denser than the granitic continental rock, and basalt that has cooled and thickened over tens or hundreds of millions of years becomes denser still. Dense enough, eventually, to be heavier than the mantle rock below it. And when that happens, when the oceanic plate reaches a subduction zone, a trench, a margin where two plates meet, the dense oceanic plate bends downward and sinks into the mantle. It peels away from the surface and descends slowly into the hot interior of the Earth, and as it descends, it pulls. The weight of the sinking slab of cold, dense rock pulls the rest of the plate along behind it, the way a heavy tablecloth dragged off one end of a table pulls the centerpiece and the glasses with it. This is slab pull. The geodynamicists Donald Forsyth and Seiya Ueda worked out the balance of forces in 1975, comparing the motion rates of plates and finding that the plates with the longest subducting slabs attached to them moved fastest. The Pacific plate, with subduction zones along much of its western margin, moves faster than plates without attached slabs. The evidence pointed clearly: slab pull, not ridge push, is the dominant driver of plate tectonics. The continents don't move because they are being pushed from the spreading ridges. They move because the oceanic plates around them are being pulled down into the mantle, and the continents riding on those plates are dragged along. The spreading ridge is less a motor and more a wound, a gap that fills as the plates move apart, driven by the pull at the other end. This is why the continents can never sit still. as long as the cycle continues. As long as oceanic crust forms at ridges and cools and densifies as it ages and eventually subducts, as long as that cold slab sinks into the mantle and exerts its pull, the plates must move. There is no stable configuration that allows rest. The engine runs because cold rock sinks. And cold rock sinks because it is cold, and it is cold because it formed at the surface and has been moving away from the warmth of the ridge ever since. The motion is self-perpetuating. Cooling drives sinking, sinking drives pulling, pulling drives spreading. Spreading makes new crust that will cool and sink in its turn. The cycle turns on itself, sustained by the simple physics of hot things rising and cold things falling. J. Tuzo Wilson, the Canadian geophysicist whose name the broader oceanic cycle carries, had a crucial insight about how this engine works over long timescales. In 1966, he published a paper in the journal Nature with a question for a title. Did the Atlantic close and then reopen? It was not a rhetorical question. Wilson had noticed something peculiar about fossils and rock formations on opposite sides of the modern North Atlantic. They matched in ways that could not be explained if the Atlantic had always been as wide as it is now, but that made perfect sense if the Atlantic had once been closed and had opened, then closed again, and then reopened. The matching fossils were not proof of a single long continuous ocean across which life had somehow exchanged. They were proof that there had been a previous ocean, the Iapetus Ocean, that had opened and then been consumed by subduction, drawing the same continental fragments back together, crushing them into the mountain belt whose remnants are the Appalachians, the Caledonides, the Anti-Atlas, before those same continents rifted apart again to open the modern Atlantic in a slightly different configuration. This was a new idea, not just that continents drifted, which by 1966 was becoming accepted, but that individual ocean basins opened and then closed repeatedly in a cycle of their own. That the same piece of continent could be on one side of an ocean, then find itself on the same side as its former neighbor after the ocean closed, then drift apart again as a new ocean opened in roughly the same place. Wilson framed this as a cycle now called the Wilson cycle. Oceans are born at continental rifts, grow as spreading proceeds, age as their floors spread out and cool, and die as subduction consumes them from one or both margins, bringing the bordering continents together in collision. The supercontinent cycle is, in essence, many Wilson cycles running in coordination. Many individual ocean basins opening and closing in a choreography that, when viewed at planetary scale, produces the rhythm of supercontinents assembling and dispersing. The Iapetus Ocean is a good example of the Wilson cycle in action. Iapetus opened when Rodinia began to break apart around 750 million years ago, separating what would become North America from what would become Europe and parts of Africa. It grew. Life evolved in its shallows and depths across hundreds of millions of years. And then, beginning around 450 million years ago, subduction began to consume it from both sides, drawing the continents toward each other, raising the mountain belts whose roots are still visible today. The Appalachians on the American side, the Caledonides on the European and Greenlandic side, and the Anti-Atlas in what is now Morocco, which was part of Africa in the closing geometry. Iapetus shrank and finally closed, bringing the continents together in a collision that formed part of the early structure of Pangaea. And then, after Pangaea itself broke up, beginning around 200 million years ago, the rifting happened in roughly the same region, but not precisely the same line, and the modern Atlantic opened, with the Appalachians and the Caledonides and the Anti-Atlas already on its shores as relict witnesses of the earlier ocean they had helped to destroy. The ocean that existed before the modern Atlantic is often called the Reich Ocean, which succeeded the Iapetus in the southern hemisphere and was involved in the later stages of Pangaea's assembly. It too is gone, consumed by subduction, its floors recycled, its record surviving only in the rocks at the margins of the continents that once bordered it. Wilson's cycle does not just describe how one ocean opens and closes, it describes the persistent tendency of the same zones of continental weakness to become the sites of repeated opening, the same suture zones to be sites of repeated collision. The planet has preferred paths, preferred lines of weakness, and preferred lines of convergence, though they shift with each iteration. The way Pangaea assembled is worth pausing on because it illustrates a concept that at first seems almost too simple to be real, and then, once understood, feels like one of the stranger things in all of geology. The question of how a supercontinent assembles has two broad possible answers, and they are called introversion and extroversion. They describe the fate of the ocean that existed when the previous supercontinent broke up. When a supercontinent fragments, it opens new ocean basins between its pieces. They'll call them the interior oceans, the young oceans that fill the space between the newly separated continents. As the fragments drift apart, those interior oceans grow, but there is also an exterior ocean, the old ocean that existed before the supercontinent, the global ocean that surrounded it. In the case of Rodinia, that exterior ocean is sometimes called the Mirovia. The question, as the cycle begins to reverse and subduction draws continents back together, is which ocean gets consumed? If the interior ocean, the young ocean that opened during the breakup, is the one that gets closed by subduction, then the same continents that drifted apart are drawn back together roughly the way they started. The supercontinent reforms by inverting itself, closing the wound it opened. This is introversion. If the exterior ocean, as the old global ocean on the far side of the drifting fragments, is the one that gets consumed, then the continents assemble from opposite sides. Fragments that were on one side of the old supercontinent end up neighboring fragments from the completely opposite side. The planet turns itself inside out. What was the far side of the world is now adjacent. New neighbors, unrelated in the previous arrangement, are pressed together into new mountain belts and new collision zones. This is extroversion. Pangaea is generally argued to have assembled by extroversion. The Iapetus Ocean and the Reek Ocean, the exterior oceans, were consumed. The fragments of Gondwana and Laurasia, themselves large southern and northern agglomerations, were drawn together by the subduction of oceanic floor on the far side of the globe from where the interior seas had opened, bringing together pieces of continental crust that had never previously been in contact. Gondwana, the great southern landmass, and Laurasia, the great northern landmass, collided along what would become the Variscan-Hercynian mountain belt in Europe and the Appalachian Ouachita belt in North America. The result was Pangaea, but the assembly was not a simple closing of a gap. It was a turning of the world inside out, a rearrangement so fundamental that the geography of the new supercontinent bore little resemblance to the geography of the old one. This has a consequence that deserves a moment's quiet attention. Each supercontinent is not merely a reassembly of the same pieces in the same positions. Each one is a new configuration, a new geometry of the same raw material, shaped by which ocean was consumed and which fragments ended up as neighbors. Pangaea was different from Rodinia not only because hundreds of millions of years of erosion, sedimentation, biological evolution, and tectonic activity had altered the fragments themselves, but because the very arrangement of those fragments was new, a product of extroversion, of a world turned inside out and pressed back together in a different face. Rodinia had its own arrangement, different again. Nuna another. Each supercontinent is unique. The cycle repeats in its broad structure. Gather, shatter, drift, gather again, but never precisely in its details. And there is something about the Wilson cycle and the introversion-extroversion distinction that points toward one of the deepest open questions in the whole field. What decides which ocean closes? What tips the balance toward consuming the interior ocean versus consuming the exterior one? The answer involves the geometry of subduction zones, the relative ages and densities of the competing ocean floors, the inherited structure of the continental margins, and, perhaps most importantly, the behavior of the deep mantle, which is where the story, in its next movement, will descend. Because the slab pull and the Wilson cycle and the introversion-extroversion question all connect, ultimately, to what is happening at the base of the mantle, to the immense, slow, poorly understood structures that may be setting the tempo of the whole planetary rhythm. But before the descent into the mantle, it is worth holding for a moment the sheer depth of the time just traversed in this part of the story. Nuna assembled 1.8 to 1.6 billion years ago. Rodinia assembled 1.3 to 0.9 billion years ago, fragmented 750 to 630 million years ago. Between them, hundreds of millions of years of tectonics, of ocean opening and closing, of mountain building and erosion, of sediment accumulating on continental shelves, of the slow accumulation of oxygen in the atmosphere, of life, at first microscopic and unhurried, evolving in those warm, shallow seas. Then Pangaea, debated, possibly short-lived, a brief gathering between 630 and 570 million years ago, or perhaps not a true supercontinent at all, but a large regional cluster, the matter still unresolved. And then the slow reassembly toward Pangaea, completed roughly 335 to 300 million years ago. This is not a simple sequence of events. It is a rhythm measured in hundreds of millions of years, in intervals that dwarf anything the human scale can hold directly. The only way to feel the scale is to let it be large, to allow it to press gently outward past the comfortable limits of the imagination and become, if not comprehensible in the ordinary sense, at least present. A vast darkness in which the continents drift like slow embers, gathering warmth and scattering, gathering again, changed each time by the journey, carrying in their rocks the compressed record of every ocean they have ever bordered and every mountain they have ever raised. The engine that drives this, slab pull, Wilson cycles, the geometry of introversion and extroversion, is not a recent invention of the planet. It has been running, in some form, for at least 2 billion years and quite possibly longer. The question of when plate tectonics began on Earth is itself one of the genuinely open questions of geology. Some researchers argue for a very early start, more than 3 billion years ago. Others suggest that early Earth operated under a different tectonic regime, and that the modern style of subduction-driven plate tectonics began sometime in the Proterozoic, perhaps around 3 billion years ago, perhaps closer to 2. The Jack Hill zircons, those 4.4 billion-year-old crystals, show chemical signatures consistent with the presence of liquid water and even of some kind of crustal differentiation at that very early time. But whether they indicate true plate tectonics or some other tectonic mode is not settled. What is settled is that by the time Nuna was assembling 1.8 billion years ago, something recognizable as plate tectonics was running. The evidence for that is in the origins, the mountain belts, preserved at the edges of the ancient cratons, showing the kinds of pressures and temperatures and geological structures that only occur in genuine subduction zones and continent-continent collisions. The engine was running. It has been running ever since. And somewhere in the deep mantle, in structures that the engine itself has organized over billions of years, the tempo of the cycle may be set. That is the direction the night's journey will take next. Down toward the blobs of hot rock at the base of the mantle, the continent-sized structures that may be the deepest part of the mechanism, the long-period oscillators around which the whole planetary heartbeat is organized. But that descent belongs to the next movement, which follows as quietly and as certainly as the continents themselves follow the pull of cold rock sinking into the dark. And so the journey goes down one final level. Past the mountains and the ocean floors, past the subducting slabs and the spreading ridges, past even the upper mantle through which those slabs descend, down to the very base of the mantle, nearly 3,000 kilometers beneath the surface, where the rock is so hot and under such pressure that it behaves in ways that have no easy parallel in ordinary life. Down there, in the deep dark at the boundary between the mantle and the iron core, two structures sit that geologists have named large, low shear velocity provinces. The name is technical and precise, as geological names tend to be, but the things themselves are neither small nor forgettable. Each one is roughly the size of a continent. Each one is a region where seismic waves, the ripples of earthquakes moving through the planet's interior, slow down measurably, suggesting that the rock there is hotter or differently composed, or in some way distinct from the mantle surrounding it. One of these structures sits beneath the African continent, the other sits beneath the Pacific Ocean, roughly on the opposite side of the planet. And they have been sitting there, in those approximate positions, for a very long time. Trond Torsvik and his colleagues, working with the record of where volcanic plumes reach the surface and sampling diamonds that carry tiny fragments of deep mantle rock up toward the light, found in 2010 that the plumes feeding the largest volcanic events in Earth's history, the so-called large igneous provinces, the events that produce vast floods of lava across whole regions, appear to originate at the edges of these two structures. The plumes rise from the margins of the blobs as if the blobs themselves are generating or focusing the heat that eventually erupts at the surface. And when the positions of those ancient eruptions are mapped back in time using paleomagnetism to place the continents where they stood when the lavas flowed, they cluster again and again above those same two deep structures, which suggests that the large low shear velocity provinces are not random. They are not a coincidental feature of the mantle. They appear to have been there in something like their present configuration through multiple supercontinent cycles. They may be, in some sense, the fixed points around which the whole rhythm organizes. Think of it this way: if you were watching the surface of Earth from far above, watching the continents drift over hundreds of millions of years, you would see them gather and scatter and gather again. And if you could simultaneously watch the deep mantle, you would see that the gathering always happens roughly above those two hot structures. Supercontinents tend to assemble above what is beneath the Pacific and beneath Africa, or more precisely, they assemble by closing oceans, and the closing is organized partly by the heat rising from those deep margins, which pushes plumes upward that eventually rift continents apart, initiating the dispersal that makes room for the next assembly. The blobs organize the dispersal sets up the assembly, and the assembly, once complete, sits for a time over a region of mantle that has cooled, then begins to be rifted apart again by plumes rising elsewhere, and the cycle continues. Not perfectly, not mechanically, but rhythmically, in the way that a living heart is rhythmic, variable, responsive to conditions, but persistent, with a recognizable beat that returns. This is why the heartbeat metaphor is apt and also imperfect, and it is worth dwelling on that imperfection because it is part of what makes the science honest. A heartbeat is regular in the way a clock is regular, one beat following the last in nearly the same interval, the interval set by the electrical system of the heart rather than by the circumstances the heart finds itself in. The supercontinent cycle is not like that. The intervals between supercontinent assemblies vary. Some estimates place the full cycle at roughly 300 million years. Others argue for 400 to 600 million years. There is even discussion of a longer envelope, a supercycle of perhaps 700 million years, within which shorter rhythms nest. The variation exists because the cycle responds to conditions, to how much oceanic crust is present, to how cold and dense the subducting slabs are, to the configuration of the continents themselves, which affects how heat escapes from the mantle and how quickly new ocean floor forms. So calling it clockwork is a useful shorthand, a way of gesturing at something genuinely periodic, but the honest version is that it is quasi-periodic, rhythmic without being metronomic, patterned without being perfectly regular. And perhaps that is more beautiful, not less, a planet that breathes rather than ticks. There is another subtlety at the deepest level that deserves its quiet moment in the night. It is called true polar wander. The phrase sounds like something from navigation, and in a sense it is, but what it describes is stranger and more vertiginous. The Earth has a spin axis, line around which it rotates, passing through the geographic north and south poles. That axis is not fixed relative to the solid body of the planet. If mass is redistributed significantly, if, for example, a supercontinent assembles in one hemisphere and adds substantial weight there, the entire solid Earth can rotate relative to its spin axis, repositioning the mass toward the equator, where rotation is most stable. The poles do not move relative to the stars, but they move relative to the rocks. A continent can appear to shift its latitude not because it has moved through the mantle, but because the whole planet has rotated around it. This is true polar wander, and it adds a layer of complexity to paleogeographic reconstruction that researchers like Ross Mitchell have spent careers trying to untangle. It means that reading ancient magnetic inclinations in rocks must account not only for the motion of individual plates, but for possible wholesale rotations of the planet itself. The supercontinent cycle and true polar wander may be linked, each episode of assembly potentially triggering a redistribution of mass large enough to rotate the planet. The ground beneath you is not just drifting laterally. Across deep time, the planet itself may have rolled. And all of this, the blobs, the plumes, the quasi-periodic assembly, the polar wandering, is the engine running beneath ordinary geography, beneath the mountains and the rivers and the shorelines that seem to define a stable world. The continents feel still because they move slowly. They feel permanent because a human life is shorter than it takes a continent to travel the length of a football field. But the stillness is an illusion of time scale, the same illusion that makes a flame seem solid when its actual substance is constantly moving. What the supercontinent cycle has done to life on this planet is, if anything, more astonishing than the mechanism itself. Because the cycle and life have not run in parallel indifference. They have collided repeatedly in ways that shape the history of living things as profoundly as any evolutionary pressure. The clearest example, and perhaps the most dramatic, begins with Rodinia. Rodinia, remember, was assembled in the tropics, spanning the equatorial region of the planet during the Proterozoic. When it began to fragment, roughly 750 million years ago, the breaking apart opened new coastlines and new seas. Exposed coastal rock, with the silicates that make up continental crust, began to weather. Rainwater, slightly acidic, dissolved the silicates in a chemical reaction that also consumed carbon dioxide from the atmosphere. As the fragmenting Rodinia presented more and more fresh coastline to tropical rainfall, more and more carbon dioxide was drawn out of the air. Carbon dioxide is a greenhouse gas. Removing it cools the planet. And the planet, in those millions of years following Rodinia's breakup, cooled. It cooled a great deal. At some point, the evidence suggests around 717 million years ago, it crossed a threshold from which there was, for a time, no return. Ice began to form. The ice reflected sunlight back to space, cooling the planet further, forming more ice. Glaciers advanced from the poles toward the equator. The oceans froze at their surfaces. The planet entered what geologists now call snowball Earth, a state in which ice may have covered the entire surface, from pole to equator, for millions of years. The evidence for this is in ancient glacial sediments found at locations that, when their paleolatitudes are reconstructed using paleomagnetism, were at or near the equator when the ice was deposited. Glaciers at the equator, a frozen world. Paul Hoffman and his colleagues argued in 1998 in the journal Science that this snowball Earth was real, and that it ended only when volcanic activity, continuing beneath the ice because the mantle does not stop for a surface freeze, gradually pumped carbon dioxide back into the atmosphere over millions of years until the greenhouse effect warmed the planet past the melting threshold and the ice released catastrophically. The melt was not gradual. Once the ice began to go, it went quickly, and the planet swung from deep freeze to extreme warmth in what was, geologically speaking, a very short time. The aftermath of that swing in the period between roughly 635 million years ago and the beginning of the Cambrian around 540 million years ago is the interval that saw the rise of complex, multicellular life. The first animals, the earliest creatures with distinct body plans. It is possible, and many researchers argue it is likely, that the extreme environmental disruption of the Snowball Earth episodes, and there may have been more than one, within the interval from 717 to 635 million years ago, created the selection pressure that pushed life toward greater complexity. That the frozen world, a consequence of Rodinia's breakup, was the crucible from which animals emerged. A supercontinent dispersed, drew the planet into ice, and in the aftermath of that ice, life as we know it began. The connection between the supercontinent cycle and the history of life does not end there. Pangaea's story runs in a different direction, not toward ice, but toward extinction. By the time Pangaea had fully assembled, roughly 252 million years ago, Earth was a very different world from the one that had existed before. The vast, shallow seas that had rimmed the earlier, separated continents, the seas in which coral reefs grew and marine invertebrates diversified over hundreds of millions of years, were squeezed and reduced as the land masses came together. Continental shelves overlap and collide, shallow coastal seas drain and disappear. The reduction of shallow marine habitat alone would have stressed the creatures living there. But something else was happening at the same time, something that the rock record preserves in the form of a vast field of volcanic basalt across what is now Siberia. The Siberian Traps. The name refers to the stepped, staircase-like landscape that flood basalts create as they pile layer upon layer. Trap being the Swedish word for stairs, carried into geology by Swedish naturalists who described similar landscapes in their own country. The Siberian traps erupted over an interval of perhaps 1 million years, centered on the end Permian boundary at 252 million years ago, and they produced a volume of lava covering roughly 7 million square kilometers to a depth of several kilometers in places. The eruptions were not volcanic in the familiar sense of a mountain that builds and blows. They were flood basalts, vast outpourings from fissures in the crust, covering the landscape in lava flows that followed one upon the other for an almost unimaginable duration. And in the process, they released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, and they baked the coal and organic sediments beneath them, adding more carbon and more toxic gases to the air. The atmosphere warmed, the oceans acidified and lost oxygen. The shallow seas that remained, already stressed by the loss of continental shelf habitat, became hostile to the creatures that depended on them. The result was the end Permian mass extinction, the largest in the history of complex life on Earth. Approximately 96% of all marine species vanished, perhaps 70% of land vertebrate species. The event is sometimes called the Great Dying, and the phrase is accurate. The world on the other side of that extinction was emptied in a way that the subsequent Cretaceous extinction, the one that ended the dinosaurs 66 million years ago, never quite achieved. It took life roughly 10 million years to fully recover. A supercontinent assembled, and in its assembly, through the coincidence of volcanic catastrophe, at exactly the wrong moment, it nearly ended the history of complex animals before that history had barely begun its middle chapters. Pangaea's vast interior, meanwhile, had become a world of extreme climate. A mega monsoon on its coastal margins, driven by the temperature contrast between an enormous land surface and the surrounding panthalassa, and deep in the interior, thousands of kilometers from any coast, a desert of a scale that has not existed since. Moisture that falls on the coast of a normal-sized continent can travel inland. Moisture that falls on the coast of a supercontinent evaporates long before reaching the center. The interior of Pangaea was not merely dry, it was hyper-arid in a way that has no modern analogue, and the creatures that survived the end Permian extinction emerged into this strange, hot, monsoon-driven world, and began slowly to diversify again. Life and the supercontinent cycle, then, are not separate stories. They are the same story told from two angles, the geological and the biological, and the intersections are where the most dramatic chapters happen. Rodinia breaks and ice covers the world and animals appear. Pangaea assembles and a supervolcanic event nearly empties the planet of complex life. Every time the continents have gathered and every time they have scattered, the conditions for life have changed. The evolution of species is partly a response to mountains rising and falling, to oceans opening and closing, to the climate of a world reorganized by the slow gathering of land. And now tonight, lying in whatever quiet darkness surrounds you, the cycle is running. It did not pause, it is not waiting. The Atlantic is widening slowly at roughly 2 to 2.5 centimeters per year, which means that since you began listening to these words, the ocean between North America and Europe has grown by a fraction that would require a micrometer to measure. The Pacific, on the other side of the planet, is shrinking. Subduction zones around its margins, the so-called Ring of Fire, are consuming the Pacific plate, pulling it down into the mantle. The Pacific has been shrinking for a very long time, and if it continues, it will close. And when an ocean closes entirely, the continents on either side of it collide. In 2022, a team at Curtin University in Australia, led by Chuan Huang, ran the mathematics of this process forward in time using supercomputer modeling. What they found was that the most likely outcome, given current plate velocities and the geometry of the subduction zones in the Pacific, is that the Americas will travel westward and collide with Asia. Australia, moving northward, as it has been doing for millions of years, will bridge into that collision from the south. The result will be a new supercontinent, centered roughly around the Arctic, with the former Pacific closed entirely and the former Atlantic still present, though perhaps partially closed as well, depending on the model. This future supercontinent already has a name, Amasia. The Americas folded into Asia, the ocean between them gone, the land gathered once again into a single vast province. The models suggest this will happen approximately 200 to 300 million years from now. 200 million years is a number that cannot be felt, only gestured at. It is longer than Pangaea has been breaking apart. It is as long as the interval between the first dinosaurs and the world you are lying in tonight. It is deep future, as deep as the deep past the night has already descended through, Pangaea, Rodinia, Nuna, the early uncertain worlds of Kenorland and and Vaalbara. And it is as certain as anything in geology can be certain, which is to say, not guaranteed in its details, but overwhelmingly likely in its broad outlines. The Pacific will close. Some new supercontinent will form. the cycle will complete another verse. Amasia is not the only candidate. Christopher Scatese, who has spent decades mapping the paleogeographic history of the planet and projecting it forward, has proposed a model he calls Pangaea Ultima, or sometimes Pangaea Proxima, in which the Atlantic closes instead, bringing North America back toward Europe and Africa, reassembling something like Pangaea but rotated differently. In Scatese's model, the Atlantic's growth eventually slows as new subduction zones develop along its margins, and the ocean that opened when Pangaea broke begins to close again, the planet's geology introverting, following the same interior ocean back toward assembly, the way that one of the two assembly modes described earlier would predict. A different geometry, a different distribution of the land masses, but the same fundamental outcome. One great continent, where now there are 7. Novo Pangaea and Aurica are additional name models, each beginning from different assumptions about which subduction zones will dominate, which oceans will close, and which will persist. They do not agree on geography. They do agree, all of them, that the cycle will continue, that the planet will gather its land again. What is strange and worth sitting with in the quiet of the night is that the future supercontinent will face conditions that no previous supercontinent faced in quite the same way. The sun is slowly brightening. It has been brightening over Earth's entire history, delivering gradually more energy to the surface. In 200 million years, it will be measurably brighter still. The interior of the next supercontinent, cut off from ocean moisture as Pangaea's interior was, will be hotter than Pangaea's interior was. The hyper-arid desert at the center of Amasia, or Pangaea Ultima, will be genuinely extreme, possibly beyond the habitable range for complex land animals of the kind that exist today. The climate of the next supercontinent, if life has persisted that long, will be a filter through which only the most heat and drought-adapted creatures pass. Whether any descendants of present life will be among them is a question that belongs to evolution, not geology. And there is the deeper future beyond the next supercontinent, the one that geological science can glimpse only as a possibility framed in uncertainty. The supercontinent cycle runs because the mantle convects, and the mantle convects because the Earth is hot, and the Earth is hot partly because it is still releasing heat from its formation 4.5 billion years ago, and partly because radioactive elements in the mantle, uranium, thorium, potassium, decay and release energy. Those radioactive elements are slowly depleting. The Earth is slowly cooling. Some models of long-term thermal evolution suggest that at some point, billions of years in the future, the mantle will have cooled enough that plate tectonics slows and eventually stops. The engine will lose its fuel, the continents will settle, the cycle will end, not in a dramatic event but in a gradual quieting, the last supercontinent remaining, assembled not because it is mid-cycle, but because there is no longer enough energy in the mantle to break it apart and reassemble it. A planet that has finally stopped breathing. But that ending, if it comes, is so far distant, billions of years, not hundreds of millions, that it belongs to a different kind of contemplation, one that stretches even beyond the deep time the night has traveled through. Tonight, the cycle is running. The blobs of hot rock at the base of the mantle sit beneath Africa and beneath the Pacific, organizing the long pulse of the planet's interior life. Plumes rise from their margins, slowly, invisibly. The Atlantic grows. The Pacific shrinks. The continents that feel like the permanent furniture of the world, the shapes you learned in childhood, the outline of South America so familiar that its fit against Africa seems obvious once you see it, are mid-journey, every one of them, between a supercontinent that has dissolved and a supercontinent that has not yet formed. The Appalachian Mountains are the torn half of a range that also exists in Scotland and Norway and Morocco. The fern Glossopteris printed its delicate leaves into rock on 5 separate continents, that now require an ocean crossing to reach. Mesosaurus, the small, freshwater reptile that could not have crossed a sea, swam in rivers that flowed through a single land. The magnetic minerals in ancient lava, minerals that froze in place as the rock cooled, pointing to wherever the magnetic North Pole stood at that moment, preserve in their alignment the latitude of a world that no longer exists, a record written in iron, readable by instruments that did not exist when Alfred Wegener first looked at a map and noticed that the coastlines seemed to belong together. Wegener was right. He was right before the mechanism was understood, right before the seafloor stripes of Harry Hess and Fred Vine and Drummond Matthews made the proof undeniable, right before the first GPS satellite measured the speed at which Eurasia and North America are drawing apart. He died in Greenland in 1930 on an expedition to a place that is itself a piece of ancient Laurentia, a fragment of the old craton that was once interior to Pangaea. He died not knowing that he was right. The continents move beneath him as they move beneath us tonight, indifferent to whether anyone has yet understood them. The Jack Hill zircons from Australia, those tiny crystals 4.4 billion years old, carry within them the signature of liquid water of an early crust that was already differentiating, already beginning the long journey toward the tectonics that would eventually organize itself into the supercontinent cycle 4.4 billion years ago. And the cycle, however it operated in those earliest times, however different its early version was from what runs today, has been running in some form ever since. Nuna assembled and scattered. Rodinia assembled and scattered, and in its scattering froze the world. Pangaea came and went, perhaps, in its brief and contested passage. Pangaea assembled, held the world in its vast, warm desert for 100 million years, then broke and broke and broke again, opening the Atlantic, opening the Indian Ocean, pushing India northward at extraordinary speed until it crashed into Asia and raised the Himalaya. And now the world is mid-scatter, the pieces of Pangaea still moving outward, and in the mantle the forces are already accumulating that will eventually, inevitably, bring them back. The cycle is not clockwork in the strict sense. It does not tick, but it returns. Every few 100 million years, in a rhythm that is as fundamental to this planet as the rhythm of the seasons is to a human life, and as far beyond ordinary experience as the seasons would be to a creature that lived for only a few days, the land masses of the earth gather themselves into one. And then they fall apart. And then they gather again, 5 times, perhaps more, perhaps fewer, the record uncertain the further back you look. And at least one more time to come, 200 million years hence, or 300, or somewhere in that vast unmeasured interval, the Pacific will be gone and the next supercontinent will stand in the morning of its long existence. Everything solid is moving. It has always been moving. It will always move for as long as the planet retains the heat that drives the mantle's slow circulation. The ground beneath you tonight is a piece of a puzzle that has been assembled and disassembled and reassembled across 2 billion years, and it will be assembled again. The mountains you know are the ghosts of older mountains. The oceans you know are the infants of older oceans that have been completely destroyed. The continents are old, patient, and in permanent slow migration, following the pull of cold rock sinking in the dark and the push of hot rock rising to meet the light. There is a kind of peace in this if you let yourself rest in it. Not the peace of stillness, because nothing here is still, but the peace of a rhythm so large and so persistent that your own brief passage through time becomes, for a moment, something held within it rather than something measured against it. A human life is perhaps 80 years, the supercontinent cycle is perhaps 400 million, the ratio is roughly 1 to 5 million. In the time it takes one supercontinent to form, 5 million human generations live and pass. Every fear and every hope and every quiet night of listening in the dark of every one of those 5 million generations, and the continents move by perhaps 1,000 kilometers in total. Not much in the scheme of a world that is 40,000 kilometers around its equator. And yet enough to open an ocean, enough to close one, enough to change everything slowly with enormous patience without any need for hurry. The last thing the night asks you to carry with you as you rest is not an answer, but an image. The continents right now, scattered across the globe, drifting slowly apart in some places and slowly converging in others, are a single frame in a very long film. If you could watch the film for the whole 2 billion years of it compressed into a few minutes of motion, you would see the land pulse. Gather, scatter, gather, scatter, gather. The rhythmic assembly and dispersal of a planet's solid skin, organized by heat from below and pulled by cold from above, driven by forces that operate on time scales no individual consciousness can fully contain. And somewhere in that pulse, at a moment corresponding roughly to right now, a frame pauses on 7 continents arranged as you have always known them. 7 pieces mid-journey, mid-scatter, moving toward a configuration that has no name yet in the mouths of the creatures who will one day live on the supercontinent that rises from their convergence. The Earth builds, the Earth breaks, the Earth builds again. This has been its way since before the oldest rock you can hold in your hand was solid, and it will be its way long after the last of those rocks has been subducted and melted and remade into something new. The ground is breathing. You are resting on a breath held for 200 million years, and in 200 million more it will be released. Let the wisdom settle soft. The rest will come on its own.